In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself, Pranav, is here to deliver today's representation, Power Transformer Part 21. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with the cooling arrangement, that is number 2, that is ONAF cooling of transformer. The full form of ONAF is oil natural, air forced, and is generally configured for large transformers of capacity up to about 60 MVA. With the increase of transformer rating, the total loss in terms of heat will have to generate more, and at the same time, to run the transformer safely, the heat transfer rate must have to be made further increase. However, heat transfer can one way be increased by the increase of the heat transfer coefficient between outside surface of the radiator and air. Heat dissipation would therefore obviously be enhanced if dissipating surface is increased, but it can be made further faster by applying forced air flow on that dissipating surface, as because the forced air, if it is blown onto the cooling surface of the radiators, then the heat transfer coefficient would have become significantly increased. So, fans are thereby designed to deploy for blowing air on the cooling surface of the radiators. Forced air takes away the heat from the surface of the radiator and provides better cooling than natural air. As the heat dissipation rate is much more faster as compared to ON type cooling, so power transformer can have to cater more load without exceeding the permissible temperature limits. However, optimization of performed dimensional parameters of radiator banks are thus to be designed with the exact configuration of fan position, fan size, and oil flow rate on the cooling capacity of radiators. In power transformer, having equipped with ONAF cooling system, the cooling reliability should have evaluate the effect of cooling performance of radiators with respect to effect of air blowing direction. As per design requirement, if the fans are relatively smaller in size, then horizontal blowing, that is in figures 96, would have to be much more effective than that of the vertical blowing configuration, as the sideways leakage of air is comparatively much less for horizontal blowing. So, in horizontal blowing, the size of the fan is much smaller. While using fans of larger capacity than bottom mounting design, which blow air from bottom to top, that is in figure 97, would have to prefer, since it is easy to design the support structures for mounting the fans below the radiators. But fans which are to be mounted with support structure against the radiator banks must have to maintain low noise and vibrations, as because both would have been superimposed on the transformer itself. Based on cost benefit analysis, a typical combination of ON-AN or ON-AF cooling arrangement can be implemented by providing temperature sensing switches to make the fans on and off in accordance with the rise of oil temperature. See the diagram. Forced airflow, cooling fans, oil natural air force type. This is the horizontal air blowing system. This is forced air from the bottom side. Now, number 3 cooling arrangement, that is OF-AF type cooling of transformer. OF means oil forced and air forced, AF cooling system, where air and oil both are to be deployed for forcibly cooling the transformer comparatively of higher rating. In oil natural air forced cooling system of transformer, the heat dissipation is accelerated by using forced air on the dissipating surface, but circulation of the hot oil in transformer tank is natural convectional flow. Again, I repeat, in oil natural air force cooling system of transformer, the heat dissipation is accelerated by using forced air on the dissipating surface, but circulation of the hot oil in transformer tank is natural convectional flow. In that case, the oil flow rate is relatively low, and obviously the heat dissipating capacity of the oil is also low. The heat dissipation rate can be still increased further if this oil circulation is accelerated by applying some force. In oil forced air forced cooling system, the oil is forced to circulate within the closed loop of transformer tank equipped with detachable radiator banks by means of using external oil pumps, and simultaneously, in order to get a higher heat transfer rate, fans have to be always operating at the radiator sections. However, both pumps and fans are automatically controlled and are to be operated either separately or in combination as corresponds to load and temperature of the transformer. Two types of oil pumps are categorically used to circulate the oil in high rating transformers, that is axial flow type and radial flow type, and type selection has to be designed as per requirement of heat dissipation capability. Axial flow inline type oil pump is usually used while transformer is equipped with mixed cooling arrangement of ON-AN, ON-AF, OFWF having coupled with temperature sensors to switch on and off of the air blower and oil pumps. Axial flow of pump can suitably serve the purpose, as because in this case, oil offers less amount of flow resistance during when and when AF cooling criteria. Radial flow pumps are specially used in cases of cooling application, OFWF and ODAF for most of the large rating power transformers where higher head is needed to develop for the oil to air heat exchangers or oil to water heat exchangers. The main advantage of OFAF system is that it is quite compact system, and for the same cooling capacity, OFAF would have to occupy much less space than when in and when AF system of transformer. Again, I repeat, the main advantage of wave AF system is that it is quite compact system, and for the same cooling capacity, wave AF would have to occupy much less space than when in and when AF systems of transformer cooling. Actually, in oil natural cooling system, the heat comes out from conducting part of the transformer is displaced from its position in slower rate due to convectional flow of oil, but in forced oil cooling system, the heat is dissipated from its origin as soon as it comes out in the oil. Hence, rate of cooling becomes faster. See the diagram. Axial flow pump, flow oil pump, winding core, forced air flow, cooling fans, oil forced air force, cooling arrangement. Now, the exact system, that is motor operated pump, flow indicator, etc., etc. The actual arrangement. Oil forced air force transformer, physically, say wave AF transformer cooling method. A transformer fitted with oil circulation pump and heat exchangers can be seen where pumps are fitted at the bottom and oil is forced to air heat exchangers. OFWF cooling of transformer. OFWF means oil forced, water forced cooling method in transformer where hot oil is passed through a water heat exchanger, which is typically designed with a shell and a bundle of tubes inside it. Heat exchangers are comprised of shell and bundle of tubes, which would have to work that one fluid, that is oil, runs through the tubes and another fluid, that is water, flows over the tubes. Transferring the heat is made through walls of the tubes between the two fluids. The oil pressure must be kept higher than that of the water, as because if there is any leakage in the oil tube, then oil alone will pass through the mix with water only, and in no way of water leaking into the oil. To eliminate any possibility of water leaking into the oil, a dedicated oil water differential pressure gauge with appropriate tripping protection system must be implemented before commissioning of this cooling arrangement. Oil to water heat exchangers are normally used in case of transformers with very large capacity, mainly installed to hydroelectric plants where abundant flow of water is always available. Basic inputs are to be needed for technical designing of transformer heat exchangers and selection of pump capacity. One, what to use, that is indoor type or outdoor type transformers. Ambient temperature and environmental factors. Optimum cooling requirement. Type of water used. Supplied water pressure and temperature. Transformer tank, oil temperature rising phenomena. Transformer tank oil temperature rising phenomena. Requisite oil pressure. Oil water differential pressure with suitable tripping sequence. How far heat exchangers are to be placed. Transformer radiator banks can be eliminated and tank size also can be reduced as the surface heat transfer coefficient of water is more than that of air, and the heat dissipation surface area would have to be made further enhanced by placing the heat exchangers far from the transformer tank. So, during designing of heat exchangers and pump capacity, basic inputs such as ambient temperature, optimum cooling requirement, supplied water pressure and temperature, transformer tank oil temperature, requisite oil pressure, oil water differential pressure with suitable tripping sequence, how far heat exchangers to be placed, that is all subjective data are to be considered for better optimization. Again, I repeat. So during design of heat exchangers and pump capacity, basic inputs such as ambient temperature, optimum cooling requirement, supplied water pressure and temperature, transformer tank oil temperature, requisite oil pressure, oil water differential pressure with suitable tripping sequence, how far heat exchangers to be placed, that is all subjective data are to be considered for better optimization. That is better system optimization, cooling system optimization. For maintaining excellent oxidative stability of the dielectric oil, heat exchanger tubes must be made of oxidation-proof materials. Most commonly selected materials for heat exchangers are copper and aluminum. Though copper has lower flexibility than aluminum, but design engineers must have to prefer copper as because the metal has the property of better sagging resistance, best possible thermal conductivity, and good oxidation resistance even when exposed to water. See the diagram. Cell and tube heat exchanger. Baffles are used in shell and tube type heat exchanger for supporting the tube bundles. Baffles are placed on the shell side space for facilitating shell side fluid to have a cross flow direction so as to instigate more intensive heat exchanges between the fluids, of which one flows through the tubes and the other flows through outside the tubes, but inside the cell. Installing baffle in heat exchangers has to increase the turbulence of the cell side fluid, but in turn, pressure of the fluid would have been dropped. The function of the cross baffle is to direct the flow across the tube bunches as well as to have a rigid mechanical support of the tubes against sagging and possible vibration. However, designed with lesser number of baffle may have to create poor distribution of fluid in cell site. Again, I repeat, however, designed with lesser number of baffle may have to create poor distribution of fluid in shell site. Each baffle should have a thickness of at least twice as thick as the wall of the tube. Baffles are commonly made of copper or naval brass and are held in positioned by means of baffle spacers. The disturbance between adjacent baffles is called baffle spacing, and closer be the baffle spacing, greater will be the heat transfer coefficient by introducing higher turbulence, but at the same time, more will be a pressure drop of the cell side fluid. As per capacity of the heat exchanger, the baffle spacing is usually configured with 0.2 to 1 times of the inside cell diameter. Cell and tube type heat exchangers is an indirect contact type heat exchanger and usually meant for high pressure applications. Designing and installation of a maximum efficiency heat exchanger will obviously have an immense impact on the operational features of a large capacity power transformer having configured with cooling methods OFWF. The design of cell and tube heat exchangers are configured with a combination of mechanical design and thermal design. The mechanical design is basically comprised of the design of main cell under internal and external pressure drop, tube bundle design, baffle design, etc. The thermal design is so far been immensely involved in evaluation of required effective surface area and number of tubes to be ascertained by calculating the log mean temperature difference. OFWF cooling arrangement. say externally installed shell, tube type heat exchanger, water outlet, water inlet, oil inlet, hot oil flow, etc. Now, ODAF cooling. ODAF or oil directed air forced cooling of transformer can be considered as the improved version of OFAF and is well preferred for cooling method in most of the large rating power transformers. In OFAF cooling condition, the oil is forced into the transformer and its flow is governed by the least resistance path as well as by the buoyancy effect. Thus, a part of the oil may not enter either in windings or core and rather would have to form a parallel path outside of these two. But the heat dissipation rate can have to be further enhanced if forced circulation of oil is directed to flow through predetermined paths in transformer windings. This concept of cooling for ensuring faster rate of heat transfer from the core and windings is termed as ODAF, oil directed and air force type cooling. However, a drop in oil pressure phenomena may have to occur because of the ducting system of each layer of the winding layer, which has to provide for directing the oil flow. If somehow the ducting system gets smeared with sludge, then may have to act as a barrier to the heat transfer from the core and coils to the coolant. In the absence of proper oil flow rate rather, for a longer duration of operation may lead to an unreasonable temperature rise and consequently the insulation between the turns of the transformer windings gets damaged. Due to deterioration of the conductor insulation, there may be a chance of occurring short circuits between the turns, resulting a sudden breakdown of the transformer. Illustration of non-directed oil flow as per figure 103A. According to the method of natural oil circulation with having non-directed oil flow design that has to utilize the thermal head produced by the heating of the oil, which rises through the heating effect of the windings. Number two, in non-directed oil flow design, flow of oil through the radial and horizontal ducts, which therefore to be connected at the axial ducts above and below, is solely dependent on thermal and turbulence effects of the oil itself. Last one, it has also been exhibited that the rate of oil flow through these radial and horizontal ducts would have much less as compared to the flow through the axial ducts. Illustration of illustration of directed oil flow as per figure 103B. In case of forced and directed circulation method, oil is to be fed by means of pump to a manifold at the bottom of the windings in a most coordinated way so as to maintain an appropriate portion of the individual main windings. To ensure considerable oil flow rate in all parts of the winding turns, there would have been implemented to insert oil flow washers at intervals in the winding layers, which alternately may have to close off the outer and then the inner axial ducts so that oil in its passage through the winding layer must follow its way like a weave or crisscross through the horizontal ducts. See the diagram. A non-directed oil flow and directed oil flow. Is the axial duct, radial ducts between the turns. This is one barricade there. There is another barricade. ODWF, cooling transformer. ODWF, oil directed water forced cooling of transformer, is an upgraded version of ODAF, and only difference is that here the hot oil is cooled in cooler by means of forced water instead of forced air. In order to implement the directed oil flow cooling of the windings, necessary estimation would have to be achieved by assessing the comparative thermal profile of the oil and windings within the transformer at rated load and allowable overload conditions. However, thermal profile must be related with the corresponding temperature conditions within the transformer, which has also to depend on transformer's losses. In addition to the ODAF cooling system, the capacity and compactness of the water heat exchangers for ODWF cooling arrangement should be determined on the basis of heat demand of the individual transformer unit with the aspect of its operating sequence, especially in an allowable overload regime. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.